And now let's hear from not a neural network, but our expert. Our opening presentation, Professor of Electronics and Communicational Sciences Chair, Swagatam Das, Indian Statistical Institute.
Навигация по ландшафту.
His topic is navigating the landscape of generative AI, large language models, and their transformative role in scientific exploration. Thank you very much. Over to you.
Good morning, and thank you one and all for extending the kind invitation to this wonderful AI Journey conference. Since I am the opening speaker, I intend to give you a 360-degree view of the landscape of generative artificial intelligence that is taking the entire world by storm, and some of our experiences with the bias, fairness of these models, including their transformative role in modifying the landscape of scientific research. So let's start with brief background. Compared to the regular machine learning models, the deep neural networks provide us context-aware representation learning capability. Regular machine learning models need to have a human-intervened feature engineering and extraction technique, which will extract the most informative higher-level features from the data items or objects and then perform classification or categorization or regression. On the other hand, deep neural networks, that is their biggest selling point. They can learn the context-aware feature extraction processes by linearly or non-linearly combining the input features in a very judicious way. So when it knows, okay, the context is between car versus non-car, it will look for steering wheels, engines, etc. So, and if we look into the current deep neural networks, their modeling and inference techniques, there are two most important categories. One is the discriminative or predictive category, where the machine learning model is happy to learn a decision boundary between the two object classes. And these are called the discriminative or predictive models, the example of which is the obviously most well-known convolutional neural networks. On the other hand, there comes the generative model, where the categorization of different data objects into different classes comes as secondary, but generative models try to understand the underlying data generating distribution, or they try to estimate the probability distribution from where the data points must have been sampled. See, to a normal person, everything comes from nature. To a statistician, every piece of data, every natural object is, an instantiation of an underlying multivariate stochastic process. And if you can somehow estimate the parameters of that stochastic process, you can later on sample from that process or from that distribution. And sampling means you can generate a lot of artificial, although very realistic, artifacts from these distributions, which the deep generative models like variational autoencoder or generative adversarial network, or nowadays the stable diffusion models, all of them try to somehow estimate these underlying data generative distributions. Okay? So if you look at deep neural networks just as a nutshell, you have many kind of neural structures like fully connected feed-forward network, convolutional neural network, recurrent neural network, and so on. And different networks can take on to different kinds of output-input pairs. Like when you have, and you can view every machine learning model as a very simple mathematical equation, which is y equal to f of x. Every neural network is a highly parameterized function. That function, the difference is highly parameterized means you can control the shape, the size, the nature of the function by using lots of parameters which you need to optimize or tune. These parameters actually control what would be the shape or nature of this function. How would it transform the input x into output y? These parameters are the trainable parameters of any deep neural network. So, and based on the nature of your input, when it is a vector, the output could be a vector, like in classification. You have a matrix, the output could be another matrix. You want to transform an image into another image. The input could be a sequence of vectors, like a speech, video, or sentence, and the output is another altered sequence of vectors. So the user defines all these transformations. The user defines and gives examples of the input-output pairs. Based on these examples, the parameters of the network are updated and the network is optimized. This is the crux of any deep neural network model on which everything runs nowadays. Now, coming to probabilistic generative models, we have real world. We have the world ahead of us, where from we get real data objects, which could be photographs of our faces or something else. And the neural network model should give us synthetic observations. It could create artificial photos, artificial text, artificial data, etc., etc. These two should match. That is the goal of any probabilistic generative modeling, that I should create a model of probabilistic inference from where the samples that I artificially create should match the real-world samples. And that is also the goal of the classical density estimation. So we can think of this whole process of generative AI as transforming, like we do in all numerical methods. We start with a very simple solution, and then we go on iteratively refining that solution until we reach the best one or the closest to the actual solution. Similarly here, the deep generative models usually start from a very easy distribution, like a uniform distribution, and then it goes on transforming that distribution into this sort of a much more complicated and might be multimodal distribution that closely matches the data generating distribution. So you can look at the neural network as this transformative function which would convert one probability distribution into another probability distribution. And this is done through an indirect training process. Before I go to the LLM part, let me talk about GAN a bit, Generative Adversarial Network, which was a 2014 breakthrough. And this network is by far the most popular one in the entire landscape of generative AI for computer vision. What it does is it uses two neural networks. One is called the generator, which as its input accepts random noise vectors from some in the input latent space. These could be 100-dimensional, 50-dimensional floating point vectors with floating point numbers from some probability distribution. And the generator, through the operations like deconvolution or upsampling convolution, generates some images from these input noise vectors. On the other hand, discriminator accepts an image and outputs a score between 0 and 1 based on the goodness of the image. Discriminator has access to the real-world repository of example images. These images could be anything, but let's say our current image class is the head and shoulder image of human beings. So the discriminator knows how original human beings looks like. The discriminator, based on that, assigns a score which should be very high if its input image is like one of these real-world human face images, and the same score would be very less, close to 0, if the input image is one of like this, because the generator initially is untrained. And like a kid who is not trained to draw meaningful pictures, the generator will initially generate very poor images. Then the discriminator will be trained to differentiate between the real images and those generated by the generator. Once the discriminator is trained and updated, it's like before you teach your students, the teacher needs to be updated, and the teacher needs to have the capability of differentiating between good and bad exam scripts. Similarly, the discriminator is first updated. Based on this updated discriminator's feedback, the generator, which was hitherto generating very poor faces, will go on adjusting its own internal parameters until it could generate images which are not exactly the carbon copy of these real faces, but somewhat different, but looks meaningful, and human head and shoulder faces. That's what we expect. These two neural networks, we say, they are playing a two-player zero-sum game in the language of game theory, and gradually they reach a state when both of them cannot improve any further. We call it the Nash equilibrium state. Although there are many other issues in training of GANs, they do not easily reach Nash equilibrium, etc., etc. But you can see this very simple illustration where GAN is learning how to generate handwritten digit images starting from complete noise. So you can see near the zero epoch, it is almost complete noise. Then it learns how to arrange these pixels meaningfully to generate these handwritten digits. So in a sense, it is trying to convert noise into meaningful data. Okay? That's the reverse of the usual, that is also bounded through the second law of thermodynamics, because it's trying to generate some form of disciplined or ordered things out of chaos or disorder. And this is how the GAN images evolved with time. So when we started to have lots of GPUs and other things, you can see we have this sort of images where you can see all the wrinkles and other things in the face of the lady, although the lady doesn't exist. Okay? This is not a camera-clicked photo of any real lady, but it still is there. Similarly, we then started to have conditional generative network, or CGAN, where we could add some extra training labels with our generated data, and the same labels could go to the discriminator as well. The goal of conditional GAN was to generate images with specific conditions on them. Like, you need to generate images of human faces all wearing nice glasses. Then you should go for the conditional GAN-like systems, and they evolved into a plethora of applications, including your ground truth is this sort of a night landscape, and your input is a daytime photo. How will your input look like if you convert it into a nighttime photo? How will your sketched objects transform into real-like photographed artifacts? If some portions from your image are missing, can you fill it up with extra pixels from the surroundings? This is an example of photo in painting. Similarly, you could use such systems like conditional GAN to automatically increase the resolution of pictures in a lot of applications, especially nowadays. These SR GANs are being used in medical imaging because medical images needs to be very high resolution, and that costs a lot of money if you go to the equipment perspective. Then there comes the style transfer image-to-image translation, which started from the famous paper of Cycle GAN in ICCV 2017. And it uses two GANs in parallel manner and uses a special type of loss called the cycle consistency loss, which would translate one image into the domain of another image in an unpaired manner. You don't need to have paired images, okay? A horse and a zebra exactly in the same posture, no. It could be a lot of horse images, it could be a lot of zebra images, and it would automatically turn horse into zebra like this, by putting those stripes onto the zebra. So this is an example where you can see the cycle GAN conversion from Fortnite game to the PUBG game. So you add the PUBG style with the Fortnite, and you get this sort of an image which you cannot tell whether it's Fortnite or PUBG. Similarly, so this was the horse-zebra conversion in video form. You can have the translation. You can change the medical images in a various ways, and it's always very dangerous. You can estimate the progress of a tumor with chemotherapy by generating its future perspective images from the older time series. You can transfer the cityscapes to different modalities, etc., etc. Four most prominent paradigms of deep generative models that are extremely popular these days are generative adversarial networks for adversarial training, variational autoencoders, which would maximize the variational lower bound. Then we have the flow-based models and the diffusion models, which obviously I hope other speakers will talk in a very detailed way, where you gradually add Gaussian noise and then reverse it, okay? When you reverse it, you denoise it. So diffusion models are by far the best applicative models in multimodal language models like DALL-E and so on. And deep generative models they are being used to generate synthetic data, which have lots of applications. Okay, one of these is to avoid the class imbalance problems, where one of the target classes have very few amount of data, and you need to artificially populate that class so that the classifier may not get biased towards the minority class. When we detect a credit card fraud, when we try to detect some, disease from a set of medical images, always the rare class is minority, but that is the target class. If you have only 4 samples from the minority class and 96 samples from the majority class, only 4 medical images of the lungs which show signs of cancer, and your machine learning model misclassifies all the 4. It says all the 100 are good enough. Then your accuracy becomes 96%, and the application of this model becomes 0, nothing, because it has missed the target class. In case of such class imbalance problems, deep generative models can artificially populate the minority class and debias the machine learning model. Similarly, we have text-to-image, image-to-text conversion, image in painting, super resolution, as you saw, artificial speech and music synthesis. Some nice music were being played at the beginning of this conference, which was generated by AI, I learned. Computer graphics, rendering, and on top of it, the entire world is now fascinated about the large language models, okay? And most of them operate on the basis of this very nice quote from a great linguist in 1957, who says, "You shall know a word by the company that it keeps." So please understand, from a philosophical perspective, computers do not perceive the meaning of the word like human beings. When we hear a word like nice chicken steak or red, all these words give rise to different imagery in our brain. Sometimes a sensation of taste when we hear the name of some exciting food. Computers, on the other hand, can very quickly see a particular word teams up with other accompanying words, and creates phrases or clauses. Based on that, the computer understands what is the semantic meaning of this word. Red. Red goes with, red fire truck, Red Bull, red rose, many things. Based on that, it perceives the true meaning of the word red. And that's why the language model analysis mathematically, although a lot of heuristic works are being done, the analysis of language model is more reliant on algebra, because language is more or less algebraic. Red, bull, when you concatenate them, it's like multiplying 2 variables, x and y. And at the same time, how many times red goes with bull, or red goes with idea, or red goes with a fire truck, this frequency is also very important. So algebra plus statistics, that actually gives rise to category theory, which should be used for the proper analysis of this sort of large language models. So if I look at this, large language models are a subset of deep learning. So the idea is artificial intelligence, the bigger umbrella. Under that, machine learning. Under that, a subset is deep learning. And within deep learning, now we have large language models that intersects with the generative AI part as well. And as you can see here, and that gives rise to our baby steps towards artificial general intelligence. The traditional programming was there is a smart human being sitting there who will write all these rules and encode them through the if-else patterns in a code, like if an animal has 4 legs, 2 ears, fur, whisker, it's a cat. Then from 2012, there came the wave of neural networks, okay? And in that wave, you need to show a machine learning model photos of millions of cats and dogs and other images, Once you show all these photos of 2, 3 categories of animals, now you show it a new photo, which was not there in your example set, and ask, what is it? It should say it is a cat. This is the wave of neural networks, starting from 2012 with the publication of a great paper in ImageNet classification. And then there came the generative language models. It's like you are a very good professor, you have a student, instead of spoon-feeding the student, you ask the student, go to a library, find huge number of books out there, read about different classes of animals, and come back to me. So similarly, these language models read a huge pile of books, not books. They have a huge pile of text data through different text repositories in the internet, like the Wikipedia, PubMed, and so on. Then they come back, and now you ask it, well, you have learned about cats and millions of other concepts. What is a cat? And it should tell you what is a cat now. Not only a cat, it should tell you what is a rat, what is a mouse, what is a hippopotamus, and so on. That is the basic idea of this artificial general intelligence. So if I put it like this, large general-purpose language models are artificial entities which should interact with you like a human being who is proficient in a particular language. Of course, in the mainframe academic world and industry, it's English. And then this general-purpose language model should be customized or tailor-made for specific purposes. What does this pre-training and fine-tuning means? Let's take the example of training a dog. These slides are from, some of them are from Google Cloud. So you have this training of a dog, and you first teach it the basic postures, like sit, come, down, stay, and so on. Once it is proficient in such basic postures, if you require a special service dog, you will have to give it special trainings, like hunting dog or guide dog or police dog, etc. That is kind of fine-tuning of a language model. So first, the language model is used to solve or trained to solve diverse common NLP tasks, like classification of each sentence, sentiment analysis, question answering, summarization of a big paragraph, text generation, and so on. Then you can actually use it for specific tasks. Like we have a project from an industry where what we are doing is we are not predicting the stock prices based only on the historical stock data through autoregression or similar techniques, but rather we are collecting the perception of the company from its customers and shareholders and other potent customers through their tweets, through their short texts, and so on. Analyzing these texts and tweets, we are trying to see whether there is a high positive perception or a negative perception about this particular company. Accordingly, we are predicting the stock prices and whether there are any chances of stock collapse. That is an effect of fine-tuning these large language models. So if you look at this, you can customize. This is the one of the definitions from this Nature Reviews Physics. Some popular examples of large language models these days include, of course, GPT, PaLM 2, Lambda, Bard from Google AI, DAO 2.0, Llama from Meta, and so on. These are general-purpose language models which most of the countries are trying to, fine-tune for their specific needs, for their own regional setup, and so on. Unfortunately, OpenAI is not very open. So their foundation models are not completely coming as a public license or free version. We need to customize them for this sort of medical, this is from this MedPalm 2, where you can use this sort of an X-ray image, and then it can actually summarize the findings by, somewhat analyzing this image and so on. So at the heart of the large language model, there is a transformer architecture, and the transformer is the most important thing to understand in this particular area if somebody wants to pursue it. It is an encoding-decoding architecture. The encoder is a neural network which converts each of the words in a sentence into some tokens, some floating point numbers. And we see that a sentence goes into a latent space. This latent space is a mathematical space where each word is embedded as a particular point, and its coordinates are the floating point numbers after encoding. The decoder should sample from that latent space and should pick up the general words that should be outputted. The decoder actually assigns a probability to all the possible words that are in the vocabulary, okay? So it's an encoder-decoder. Both are neural networks, and they could have this layer-wise connection. So strangely, this latent space where the encoder encodes an input sentence is very mysterious. I try to work with the statistical basis of this latent space because it's a mathematical space, and words in different languages should come to same point or very similar points in this strange mathematical space. So whatever is the word for water in English, in Russian, in my native language, Bangla, all these words after this neural network-based encoding should come to the same point because they express the same semantic meaning. So this is just, okay. And nearly all this started with the publication of this very famous paper in NIPS 2017, which had the attention mechanism. Attention is a method of understanding how every word relates to the earlier words, okay? So as a adult human being, when you read a sentence, you don't have to read every word of it, including the articles, conjunctions, prepositions, everything. No, your brain perceives the sentence only through 2-3 main keywords picked up from here, which associate mostly to the meaning of the sentence. You don't have to pronounce and read every word. Attention is a mechanism like that, where the neural network learns this sort of weighted relation between different words in 2 different languages, or the next word with the earlier words, and so on. It's a wonderful mechanism. And we have this sort of types of large language models, including zero-shot, fine-tuned or domain-specific, language representation model, and multimodal model. By the way, GPT is just the decoder part of the transformer architecture. The encoder part, which was used for representing the language, is not open. So GPT, Generative Pre-trained Transformer, which has this series, and GPT 3.5 is the chat GPT, this is basically the decoder part, which could have zero-shot model. Zero-shot model means some concepts were not shown to the model during the training. The model was trained to understand an elephant, a zebra, a horse, etc. And during the testing time, instead of an elephant, a huge truck comes before it. So the model, from its earlier experience, should still recognize it as an elephant-like structure, something huge which is moving. Okay? So that is the zero-shot modeling. And thereby comes, okay, so ChatGPT, all of you know, I don't have to give an introduction. This is not itself a large language model, but it's some kind of interface between GPT 3.5 and the human users. And it works through this transformer architecture, fine-tuned with some module called InstructGPT. And InstructGPT includes a reinforcement learning-based mechanism of correcting its prompts, its outputs based on human feedback. That's why OpenAI employs lots of content filtering people, and they also want feedbacks from its millions of users. Any new language model should do that. And there comes prompt engineering. Now this term, sorry, marks one of the most important jobs in the domain of large language models. And it's all about how you modify how you prompt, how you ask it a question, so that it can cater to your need. Translate a sentence from English to French, let's say. The unclear prompt is just translate this. Clear and effective prompt would mean the context of the sentence, the exact sentence, and what you want to do with it. Okay? Summarize a news article. Unclear, bad prompt, that means the command you give to the language model is like, summarize this article. Effective prompt would be provide a concise summary of the main points in this news article about climate change. There is a nice paper on large language models as zero-shot learners, which gives us the hint of how chain of thought prompting or other prompting techniques could be very effective. Like when you give this sort of a question to your LLM, you should prompt it to reason step by step so that it can go through different clear steps and give you an answer. And you can see the computing steps. Usually, they do not make mistakes if they have to reason through such steps. Large language models could be very, very effective in scientific research, especially in terms of aiding in the data analysis, prediction, generating code examples, improve the code, contribute to automated reasoning, enhance communication between researchers and their collaborators, and so on. So writing a funding proposal, here is a draft funding proposal. Suppose I compose a funding proposal for the Department of Science and Technology, Government of India. So if you give this sort of a prompt, you can get a nicely written and broken into different sections. This sort of a funding proposal, you can get the clear milestones, which of course you need to carefully examine and correct and edit. But the whole format would be nicely given. Different sections would be populated with basic review-like sentences and so on. We have to keep in mind ChatGPT or similar large language models, they do not differentiate between facts and fiction, so you need to be very careful about what they have written here. Similarly, I would have to skip multiple other slides. So you can summarize a blog post. Summarize the blog post which is given here about something. You need to write the review section of your paper. You can summarize it by using a ChatGPT, and then you can, if needed, you can correct the content. Coding is most effectively assisted by ChatGPT. You can break a problem into simple modules, and the ChatGPT could actually write down the codes, explain the main concepts and loops behind the codes, the breakpoints, the debugging points, etc. It can review your code, it could assist in the language, it could guide on the project, and so on. So, for example, this is an example of writing a PyTorch network with multi-head, which was done by ChatGPT, and you can easily copy the code from here and use in your actual application. So, explaining the new concept like how does self-attention work in transformer models. These are all the way of you prompt it and it gives you some examples, it shows you nice illustrations and so on. Okay? So this way we can use it for scientific research, but we need to remember, are we ethically on the right track? Are we achieving equitable and responsible AI with LLMs? The answer is mostly no. The Turing awardee and one of the founders of deep neural networks model says 94.7% hate speech are taken down automatically by AI. We believe, and in India is a very diverse country where we do some research about the ethical perspectives, we see that the ground reality is not like that. There is unfathomable amount of training data, but size doesn't guarantee diversity. Social views can change. There is a lot of encoding bias inside, which nobody is there to correct. Curation, documentation, and accountability is a very big problem. And as a result, these are some points made by Dr. Timnit Gebru from Blacks in AI. And as a result, a limited set of subpopulations continue to easily add data, sharing their thoughts and developing platforms that are inclusive of their worldviews. Who are the contributors to Wikipedia? Mostly people from a particular sect of the world. That doesn't have contributions from people from other underrepresented countries. Africa, Tanganyika, Ghana, Nigeria. How many of those people contribute to Wikipedia? So the training data, that is huge, but that is not fully inclusive. That is the training data used for LLMs. Various forms of abusive language, harassment against different groups of people remain unaddressed, proliferating harmful content. And as a result, the huge amount of bias continue to be added. So gatekeeping is always done by those who are in power. That is where it comes to adapt such large language models, and if required, create your own foundation model in your own language. There are a lot of historical biases. I will just give you one example. I will skip through all these because the time is limited. Gender bias in performance feedback written by ChatGPT. Kindergarten teacher, almost most of the time, it will say it's a female, she. On the other hand, construction worker, most of the time, he. If you look at example of LLM bias in large PLM, so suppose you want this, write it a paragraph about your family, it will definitely write, my mom is a homemaker, my father is a doctor. It will never write, my mom is a doctor and my father cooks at home. Okay? Similarly, if you want it to associate some emotion with the sentences, he loves travel alone, the prediction is joy. She loves travel alone, the prediction is fear, because she is a lady. So these are inherent societal biases which are present inside language models, especially from these big companies, because they are using almost the entire internet. So 4 very emerging issues to overcome: bias, lack of explainability when the GPT is giving you some result, or any language model. Why the result? There should be some little bit of explainable interface there which is missing. Ethical concerns, which holds into removing the bias. Let the language model doesn't target any specific group or sect of people on the basis of religion or political, disparity and so on. Spread of misinformation, this is very, very important. It should not culminate a lot of information and give you some mixture of half-truth or no truth. And these are some of the important issues that we should be aware of. Inclusiveness in training data. Huge training data doesn't mean inclusiveness, doesn't mean it is balanced over all possible groups. Understanding cultural idioms associated with different local languages. India has 23 plus language groups. Many other countries, I'm sure, have different language groups. And, one phrase could be very humble in your language, very offensive in my language. It could be. So language is inherently related to culture. And large language models, till date, do not have a mechanism of understanding such cultural idioms behind different languages. That becomes very important when it comes to multilingual handshaking procedures. So no law enforcement based on biased ML models, we need to keep it in mind. Carbon emission is a very, very big issue because nowadays we have huge number of parameters. GPT-4 has 1 trillion parameters to train. Can we go back to neurology? Can we look back into the basic neuroscience models, how the actual neurons work, how they are surrounded by the astrocytes and glial cells, which sidewise infiltrate and regulate the information flow through sodium and potassium channels? Can these mechanisms be further embodied or simulated to create next generation LLMs where the foundation model, for training the foundation model, we don't need to look into the faces of big techno giants. And as independent researchers, you will be able to do that. Is it possible? These are some issues. Can we finally build, of course, AI-based, AI-backed technology that will decentralize power, protects our people, and offer key benefits to the members of the most marginalized communities? I believe these are some points that the young researchers, especially, who are the futures, should think. So with this, I would like to thank you very much for your kind patience. Thank you.
We can't thank you enough for taking the time to speak to our conference. A great number of questions from our audience were collected during your speech, but we only have time for one. I'll try because it's very difficult for me, many unknown words.
Okay.
What determines the rapid development of LLM? It's large language models, yes?
Yes.
Yes. Is this due to the fact that the training data is presented mainly in natural language? If so, are there more effective ways to train models that don't use the arbitrary text?
Yeah, that is specifically the question. The foundation models have become so popular since 2017 because of 2 factors. One is NVIDIA started to generate more and more of their big GPUs, huge computing power came, and the amount of digital literature, digital text in the World Wide Web became huge. Wikipedia became huge and open, made help this medical literature database PubMed, all these databases became huge, and they started to open up. So as a result of this combination, these foundation models started to grow, and they are trained on arbitrary text so much that initially, if you look back in the March, April of 2023, the outputs from ChatGPT were sometimes on the verge of being ridiculous. Gradually, through this human feedback, content filtering, huge amount of content filterers employed by OpenAI, they started to refine the responses. Now, more or less good, but in English, of course. In regional languages, it still generates very ridiculous texts and other outputs. Many of you might have seen that. So the idea is, for training the foundation model, you should also refine the underlying texts. You should cut off the arbitrary texts. You should cut off the offensive language, hate speech, other things. This task gets the need of developing new foundation models other than those which are already being fine-tuned by OpenAI and kept under their secret vaults.
Swagatam Das, we are truly grateful for the knowledge you imparted to us. Thank you. Thank you very much.
Thank you so
This
much.
applause for you. Thank you. Thank you.
So I should...
Yeah, this way. Ну что ж, друзья, вы слышали?
Right. Friends, you are hearing this music that was generated by the AI, and it was done specifically, it was generated specifically for our conference, and we are having a short coffee break, and the coffee break will be followed by the continuation of the conference. You can go to aiga.ru or .com, and you will be able to review the program. Our speakers know how to manage your expectations and the capabilities of the future, and we're seeing you here in 10 minutes. 10 minutes coffee break.